Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is a portion of distributed forces. So you must first master derivation of formulas for volumes, areas and arcs or lines, and also familiar with them. And this part will be to enhance your thinking skills, especially in locating centroids of volumes, areas, and arc lines, which are necessary later in analyzing a system with distributed forces. So level 11 problem, locate the centroid of the plane area shown. So it consists of a parabola, then less this semicircle here. So I'll just use the principle on composite areas. By symmetry, barred x is 0, so that's why we know already that barred x is 0. So we need only barred y. For parabola, which is open downward because it is indicated this is the vertex, from the vertex along the axis of symmetry to the centroid, it is 3/5 of this height, 3/5 of 3. So therefore, from the base, it is 2/5, 1 minus 3/5, so 2/5 of the base. For semicircle, the location of the centroid is, of course, 4r over 3 pi from the diameter, 4r over 3 pi along the axis of symmetry. And you should know that, or else you cannot solve this problem. Or you may solve this by integration, which is more difficult and challenging. So area of parabola is 2/3 base times height, 2/3 of 9 times 3, by the way. This is a parabola, this is the base. So the area is 2/3 of the area of the circumscribing rectangle. And I hope that you know that as a formula. If not, you derive the area of parabola first and show that it is 2/3 of base times height. So 18 square meters. Then it's YC of parabola is, as mentioned earlier, this is 2/5 of 3. Y sub C of parabola is 2/5 of 3, and it is 1.2. For the semicircle, the area is pi r square over 2, pi 1.8 square over 2, so 1.62 pi, which is to be subtracted because this is only the shaded part. Then it's y sub c of semicircle is 4r over 3 pi, 4 times 1.8 over 3 pi, and it is 2.4 over pi. So by Varignon's theorem, area net, which is area of parabola minus area of semicircle quantity times yg equals area of parabola y sub c of parabola minus area of semicircle y sub c of semicircle. So 18 minus 1.62 pi yg equals 18 times 1.2 minus 1.62 pi times 2.4 over pi. So solving for yg is 1.373, and xg, we already found it. Level 12, a uniform semicircular rod of radius r is supported in a bearing at its upper end and is free to swing in the vertical plane. Calculate the angle theta made by the diameter with the vertical for the equilibrium position. So, unless otherwise, the reaction at the pin support and the weight of this semicircular wire coincide, then there will be no swinging anymore and the system is in equilibrium, and we must define that. So the idea is the reaction at O and the weight of this semicircular wire must coincide, and they must be equal, so that if we sum of moments about any other point, it will be 0, so it is in equilibrium. The location of the centroid or center of gravity of this wire is from the diameter in the perpendicular direction is 2r over pi, if you can remember, and that is derived already. All you have to do is remember. So that's the point where the weight acts. That's the reaction, and they must be collinear as shown. So that tangent of theta, this is 90 degrees, is opposite, which is 2r over pi over this distance, which is the radius. So tangent theta equals 2r over pi over radius, cancel out r, so 2 over pi. Inverse tangent of 2 over pi, theta equals 32.42 degrees. So that's it for this problem. Level 13, determine the y-coordinate of the centroid of the shaded area. Check your result for the special case A is 0. So if you look at the figure, it is symmetric with respect to this axis, so bar the x is 0. That's why we are just asked to compute or determine the y-coordinate of the centroid. So we deal with this shaded area as area of big triangle minus area of small triangle. So the location of the centroid is there, and it is 2/3 of the height from the x-axis. For this small triangle, the location is 2/3 of A, as in the figure. So we will call the base of the bigger triangle as B and the smaller triangle as B1 rather. So from the figure, tangent of 60 degrees is opposite H over this distance, which is half of B. So B over 2. So it is also equal to A over B sub 1 over 2. So that means B is 2H over tangent 60. So it is 2 square root of 3H over 3, which is also same with B1, 2 square root of 3 over 3 of A. So the area of the big triangle is 1/2 of B times height. So 1/2 of B, which is 2 square root of 3H over 3 times height. So simplifying, cancel out 2. Area of big triangle is square root of 3 over 3H square. So same pattern as that area of small triangle. I'm not showing it here, but it is also square root of 3 over 3 A square for the small triangle. Therefore, the net area, which is area of big triangle minus area of small triangle, is square root of 3 over 3 H square minus square root of 3 over 3 A square. So as I said, I'm not showing this anymore, but the area looks the same as this based on the calculations above. So square root of 3, factor out square root of 3 over 3. So we have H square minus A square. That's the net area or the area of the shaded part. Applying Varignon's theorem, square root of 3 over 3, quantity H square minus A square equals area of big triangle square root of 3 over 3 H square times 2/3 of H minus square root of 3 over 3 A square times 2/3 of A. Cancelling out square root of 3 over 3. So we have quantity H square minus A square YG equals 2/3 of H cube minus 2/3 of A cube. So YG, therefore, factor out 2/3. H square minus A square YG equals 2/3 quantity H cube minus A cube. So finally, YG is 2 quantity H cube minus A cube over 3 times quantity H square minus A square. So that's it for this problem. XG is 0, but we are only asked for YG. Level 14. Present two methods in locating the centroid of the shaded region shown. Actually, we can present three, but two by double integration and one by composite area approach. But for the composite area approach, you need to know the location of the centroid of this parabola, or else you cannot present that solution. So remember that a parabola should start from the vertex to any end. If it is not the vertex, then you cannot use the area of the parabola and the location of the centroid of that uh, figure, which is a portion of the parabola only, but not treated as, cannot be treated as a parabola, purely a parabola. So let's have horizontal strip, the easier. And if you want to check the area by vertical strip, then do it. Anyway, you can use your high-tech calculator. So in this case, the easier integration method would be considering horizontal strip. And this is the boundary at the right, which is the equation is x equals 4, because this is 4 inches. So this line has an equation x equals 4. Just like the y-axis, the equation of the y-axis is x equals 0, because every point on the y-axis has x equals 0. The horizontal axis is, which is the x-axis, has an equation y equals 0. So the x-axis, the equation of the x-axis is y equals 0, because every point on the x-axis, the value of y is 0. So this is right x, which is 4, and the thickness is dy. So right x is 4, the left x is just x, and we use the x of this curve or this parabola, x left. So the area is the length of this strip, which is right x minus left x times the thickness. Then we're going to integrate that. Since it is y that is the variable of integration, y varies from this level 1.5 to that level 3 inches. So that's the centroid of the strip. So the x coordinate is the average of right x and left x as shown. So quantity x right plus x left divided by 2, that's the midpoint formula. While y sub c, because every element of the horizontal strip is equidistant from the x-axis, so y sub c is just y. So it is here y, at the center y, and at the right end y. So y sub c is just y. So area is integral from 1.5 to 3 of right x minus left x dy. Right x is 4, left x is 4y squared over 9. So from 1.5 to 3, integral of 4 minus 4y squared over 9 dy. So the area using your high-tech calculator there can now be evaluated, and it is 2.5 square inches. Then for x sub c, area x sub g equals integral of 1.5 to 3 of x sub c dA, where x sub c is this average here, 1/2 of right x plus left x over 2, then dA right x minus left x dy. So simplifying, xg is 2.1 over 2.5 times 2, so that would be 1.5 integral from 1.5 to 3 of right x squared minus left x squared. Substituting the value of right x, which is 4, so 1/5 integral from 1.5 to 3 of quantity 4 square minus quantity 4y square over 9 square dy. And using your high-tech calculator, we can now evaluate x sub g, which is equal to 2.940 inches. So it has sense, that's about here. That's 2.94. For barred y, it should yg it should be greater than 1.5. Rough estimate 2 inches. So area yg equals integral of y sub c dA. Y sub c is just y in the figure, and dA is this one, quantity 4 minus 4y squared over 9. So no problem in the integration because you have your high-tech calculator. 2.5 yg equals integral from 1.5 to 3. Y sub c is just y, then quantity 4 minus 4y squared over 9 dy. So this is easily evaluated by power formula. If solve manually. But I'm not presenting the manual solution because we are allowed to use the high-tech calculator. So YG is 2.025 inches. So my estimate that this 2 is very close to that. Then by the composite area approach, this area of shaded region is area of big parabola minus area of small parabola minus area of this rectangle. So area of big parabola is 2/3 of 4 inches by 3 inches. So 8 square inches. Area of this small parabola is 2/3 of 1 times 1.5. Of course, the area of the rectangle is 3 times 1.5. But before that, you need to know x sub c of parabola and y sub c of parabola. So you must be able to memorize the location of the centroid of a parabola or derive, because if you just memorize, definitely you will forget it later, especially if you do not use it frequently. So better derive it so that you can recall if in case you will forget. So it is 3/5 along the axis of parabola, 3/5 of 4, and for y sub c of big parabola, 3/8 of the height. So that's it, as long as it starts with the vertex. So x sub c of big parabola is 3/5 of 4, so 2.4 inches. Y sub c of big parabola is 3/8 of 3 inches, the height, so 9/8 inches. For the small parabola, the area is 2/3 of 1 times 1.5, so it is 1 square inch. Then x sub c of small parabola, 3/5 of 1 inch, so 3/5. Then y sub c is 3/8 of 1.5, because this is the small parabola and these are the dimensions for the small parabola. So 9/16 inch. For the rectangle, the area is 3 times 1.5 and it is 4.5 square inches. And for x sub c of rectangle, it is 1 plus half of 3, 1.5. So 1.5 plus 1 is 2.5. X sub c of rectangle, 2.5. Y sub c is, of course, half of 1.5, so 0.75. So the area is 8 minus 1, 8 for the big parabola minus area of small parabola, 1 minus area of rectangle, 4.5. So it is also 2.5 square inch here, just to check. Then apply Varignon's theorem. Area times xg equals area of big parabola 8, x of big parabola 2.4 minus area of small parabola 1, x sub c of small parabola 3/5 minus area of rectangle 4.5, x sub c of rectangle 2.5. Solving for x sub g is 2.94 inches. It's okay, it's the same. Then 2.5 yg equals 8 times 9/8 minus 1 times 9/16 minus 2.5 times 0.75. So yg of the shaded section is 2.025 inch or inches. That's it for this problem. Level 15, present two methods in locating the centroid of the shaded region shown. So this is almost similar to the preceding problem, level 14, but a bit challenging because this is no longer a spandrel parabola but an nth degree curve, third degree curve. So we use the general formula. I already derived the y coordinate of the centroid of this general curve, which was n plus 1 times height over 2 quantity 2n plus 1, And you should be able to recall that so that we will not be worried about other ways of presenting the solution. So I'll use the first one is by integration and using vertical strip. So the upper y of the curve is the y of this curve here. Lower y is the x-axis, and the x-axis is y equals 0. Therefore, the height of the strip is just y, and the thickness is dx. So the variable of integration is x. The location of the centroid is here at the midpoint. So the average of y and 0 is y over 2, of course. The location of the centroid is height of rectangular strip over 2. While the x-coordinate, because this is parallel to the y-axis, so every element of the vertical strip is equidistant from the y-axis. So x sub c is just x, as shown. And y sub c is half of the height of the strip, rectangular strip, so y over 2. Y sub c is y over 2, as shown. So by integration, x varies from 1 to 2. So area equals integral from 1 to 2 of area of the strip, which is y, height, thickness dx. Substitute the value of y, which is quantity 1 plus x cubed over 8. And using your high-tech calculator, if done manually, that's also simple because that's power formula. So area equals 47 over 32. Then by Varignon's theorem, area times x sub g equals area of this figure minus area of this small region under this curve, then plus area of the rectangle. So area xg equals integral from 1 to 2 of x sub c dA, where x sub c is just x. So 47 over 32, x sub g equals integral of from 1 to 2 of x, then y dx. This is y. So again, this is easily evaluated by power formula manually. But since our calculator is allowed, so I'll just solve it right away. So xg equals 1.549. Then area yg equals integral of y sub c dA, where y sub c is just y over 2 in the figure. 47 over 32 yg equals integral from 1 to 2 of quantity y over 2 times y dx. So simplifying, yg is 32 over 47 times 2, 94. 32 over 94 integral of y squared from 1 to 2. And y is 1 plus x cubed over 8, then quantity squared dx. So using the high-tech calculator, yg is 0.7561. So that's it for the first method. For the second method, composite area approach. So the area, we divide it into this manner, whole. So the area of this part is area of big nth degree curve area under the nth degree curve, third degree curve, minus the area of this part, which is also third degree because this is the vertex. And this part here, the total height is, substitute here 1 plus 1 cube over 8 because x is 1, so 9 over 8. So that means this part, this small height here is 1 over 8 because this is 1 plus 1 cube over 8. So 1 plus 1, 8, minus 1 because this is already 1, so that means that's 1, 8. And when x is 2, the total height here is 1 plus 2 cube over 8, so that's 2. 1 plus 1, 2. So that means the height of this nth degree curve, just this nth degree curve above this horizontal red line, is also 1. So the total height is 2. So area of big curve, I just called it spandrel, is 1/4 of 2 units times 1 unit. This is 1 unit. 2 minus 1. So 1 unit, the height. Then remember the area is in general BH, base times height over n plus 1. So the reason why this is 1/4 because the degree is 3, then there is plus 1 in the formula, and this is base, that's the height, so 1/2. The area of this small, this is our guide, the location of the centroid there, x, this x here, x sub c, is n plus 1 over n plus 2 times b. So area is bh over n plus 1, then x sub c is n plus 1 over n plus 2 times b. Then y sub c, which I derive as level 5a, I think, in the second part, I think, or in the first part, I derived the y sub c, and it was n plus 1 h over 2 times n plus 1. I think that's the formula. N plus 1 h over n plus 1 h over 2 quantity 2n plus 1. So that's it. That's our guide. But you have to derive this first so that you can remember this, or else just present integration method. So x sub c of big parabola, big shaded portion under this n degree curve is 3 plus 1 over 3 plus 2 of b, where b is 2. So 3 plus 1 times 2 over 3 plus 2, and it is 1.6. Then y sub c of big spandrel is n plus 1, 3 plus 1 times 1 over 2 quantity 2 times 3 plus 1. And take note that distance is from this horizontal line to the centroid. So because we refer it from the x-axis, then we have to add 1. So it is 1 plus this, and the only, this part is this formula here, this formula. So that's why you have to add 1. So it is 9 over 7. Obviously, it is more than 1. And for the small spandrel, it is 1/4 of 1 by 1/8. That's the height is 1/8, 1 over 32. Then its x sub c of small spandrel is 3 plus 1. This is 1 over 3 plus 2. So 3 plus 1 times 1 over 3 plus 2, it is equal to 0.8. Then its y sub c is 3 plus 1 times 1/8, because the height is 1/8 here, all over 2 quantity 2 times third degree plus 1. Then another plus 1 because it is more than 1. 1 plus this formula here. So it is 29 over 28. So 1 over 28. 1 plus 1 over 28. So that's correct. Then for the rectangle, this rectangle here, the dimension would be 1 by height 1. So it is a square. Area of rectangle is 1 by 1. So 1. Then x sub c is 1 plus half of 1, 1.5. And y sub c is half of 1.5. So applying Varignon's theorem, area net is 1/2 minus 1 over 32 plus 1. 1/2 minus 1 over 32 plus area of rectangle or square 1. So area is 47 over 32. We checks here. Then Varignon's theorem, 47 over 32 x sub g equals 1/2 times 1.6 minus 1 over 32 times 0.8 plus 1 times 1.5, x of rectangle 1.5. So xg is equal to 1.549, of course. Then 47 over 32 times yg equals 1/2 times 9 over 7. minus 1 over 32 times 29 over 28 plus 1 times 0.5 for the rectangle. So YG is equal to 0.7561. So that's it for this video. I hope that you were able to follow the solution. So it's easily understood, but for the second approach on composite areas, you need to remember the formulas, or else you cannot apply the composite area approach or method unless you can remember the location of centroids of those common areas.